Module 5. So in this module we will deal with general characteristics of queue, meaning relationships of important performance measures, estimation of mean measures of performance, effect of varying input parameters, mathematical solutions of some basic queuing models. So first one, characteristic of queuing system. Key elements of queuing system. Customers. So that refers to anything that arrives at a facility and requires service. It may be people, machines, trucks, etc. And next second one, calling population. The population of potential customers may be assumed to be finite or infinite. So finite, you have finite capacity, finite population is the finite population model. If arrival rate depends on the number of customers being served and waiting. Example model of one corporate jet. If it is being repaired, the repair arrival rate becomes 0. Infinite population model, if arrival rate is not affected by the number of customers being served and waiting. Example, the systems with large population of potential customers. Next one, system capacity, a limit on the number of customers that may be in the waiting line or system. Limited capacity, example, an automatic car wash only has room for 10 cars to wait in line to enter the mechanism. If the system is full, no customer are accepted anymore. Unlimited capacity, example, so when you consider ticket sales with no limit, all those things will be unlimited capacity. For infinite population models, in terms of inter-arrival times of successive customers, arrival times that are random arrivals, inter-arrival times usually characterized by a probability distribution. Most important models are post-on-arrival process with rate lambda, where a time represents the inter-arrival time between customers n-1 and customer n and is exponentially distributed with mean 1 by lambda. Scheduled arrivals. Inter-arrival times can be constant or constant plus or minus a small random amount to represent early or late arrivals. Example, patients to a physician or scheduled airline flight arrivals to an airport. At least one customer is assumed to always be present, so the server is never idle. Example, sufficient raw material for a machine. Queue behavior, the actions of customers while in a queue waiting for service to begin. For example, so one, that is leave when they see that the line is too long. Okay, next one, so renate, that is leave after being in the line when it's moving too slowly. Then jockey, move from one line to a shorter line. Queue discipline, the logical ordering of customers in a queue that determines which customer is chosen for service when a server becomes free. For example, first in, first out, last in, first out, service in random order, shortest processing time first, service according to priority. And we have Kendall's notation. So A, B, C and NK. A is denoting, represents the inter-arrival time distribution. B represents the service time distribution. C represents the number of parallel servers. N represents the system capacity. K represents the size of the calling population. N, K are usually dropped if they are infinite. So example MM1 infinity, so GG155, MM520, 1500 before. So all those things are examples. And then we have some formulas, that is notations, Pn. So Pn steady state probability, so that is Pn number of customers, probability that n customers in the system, Pn of t at the time t, n customers. Lambda is denoting the arrival rate. Effective arrival rate is lambda e. Rho, the server utilization. An is inter-arrival time between customers n-1 and n. Sn, service time of the nth arrival customer. Wn, total time spent in the system by the nth customer. And we have LQ of t, that is number of customers in queue at time t. L, the long run time average number of customers in system. LQ, the long run time average number of customers in queue. W, that is long run average time spent in system per customer. WQ, long run average time spent in queue per customer. And for GG1 infinity queues, any single server queuing system with average arrival rate lambda customers per time unit, average service time E of is 1 by mu time units, and infinite queue capacity and calling population. And L equal to lambda W can be updated. And we have the formulas there for single server. Rho equal to lambda by mu. P naught is 1 minus rho. L equal to rho plus rho square into 1 plus sigma square mu square by 2 into 1 minus rho. W is 1 by mu plus lambda into 1 by mu square plus sigma square by 2 into 1 minus rho. LQ is rho square into 1 plus sigma square mu square by 2 into 1 minus rho. WQ is lambda into 1 by mu square plus sigma square divided by 2 into 1 minus rho. Formula for single server infinite system. P naught is 1 minus lambda by mu. LQ is lambda square by mu into mu minus lambda. L equal to lambda by mu minus lambda. WQ is lambda by mu into mu minus lambda. W equal to 1 by mu minus lambda. Lambda is arrival rate and mu is the service rate. First question. The arrival of customers at a one window drive-in bank follows a Poisson distribution with mean 12 per hour. Service time per customer is exponential with mean 10 minutes. The space is front of the window, including that for serviced car can accommodate a maximum of 3 cars, and others can wait outside the space. Find first one, probability that an arriving customer will not wait, effective arrival rate, expected number of customers in the drive-in bank, expected time a customer spends in the drive-in bank, expected number of customers in the queue, expected waiting time of a customer in the queue. So here lambda is 30 per hour, mu equal to 20 per hour, and k equal to 10. Note that the maximum capacity k of the system equals 10 because the waiting capacity is 9 and that 1 may be treated. So that is k equal to 10. And rho equal to lambda by mu, that is 30 by 20 equal to 3 by 2 equal to 1.5. Then we have the effective arrival rate lambda dash equal to mu into 1 minus p naught, that's equal to 19.8235. And Ls equal to rho by 1 minus rho, that's equal to, we are getting 10 into 1.5 into 5 raised to 10 by minus 56.66650. Ls equal to 7.1765. The expected time a patient spends in the clinic is given by Ws equal to 1 by lambda dash Ls, that's equal to 21.72, and LQ equal to 6.1853, and waiting time is WQ equal to 18.72. Next is, a city has a one-person barber shop which can accommodate a maximum of 5 people at a time, 4 waiting and 1 getting haircut. On average, customers arrive at the rate of 8 per hour, and the barber takes 6 minutes of serving each customer. It is estimated that arrival process is Poisson and the service time is an exponential random variable. Find the percentage of time the barber is idle, fraction of potential customers who will be turned away, effective arrival rate of customers for the shop, expected number of customers in the barber shop, expected time a person spent in the barber shop, expected number of customers waiting for a haircut, expected waiting time of a customer in the queue. Rho is here, lambda by mu, that is equal to 8 by 10, that is here 0.8, and the ideal, that is P naught, you have to find the P naught, you are getting applying the formula 0.2717. Second one, you need P of n greater than or equal to 5. So when you are applying 1 minus rho into rho raised to 5 by 1 minus rho raised to k plus 1, you are getting 0.0888. Then effective arrival rate of customer lambda dash is equal to mu into 1 minus P naught, that is 7.29. Then LS we are getting rho into 1 minus rho k plus 1 into rho raised to k plus 1 by 1 minus rho raised to k plus 1. Substituting these values we are getting 1.8684 and WSS 1 by lambda dash LS equal to 15.3778 and LQ equal to LS minus lambda dash by mu equal to 1.1394 and WQ equal to 1 by lambda dash into LQ, that is 1 by 7.29 into 1.1394, that is 0.1563 hour. Next one, arrival at a telephone booth are considered to be Poisson with an average time of 12 minutes between one arrival and next. The length of a phone call is assumed to be distributed exponentially with a mean 14 minutes. First one, find the average number of persons waiting in the system. Second, what is the average number of persons waiting in the queue? Third one, what is the probability that a person arriving at a booth will have to wait in the queue? So arrival rate is 1 by 12 per minute. Service mu equal to 1 by 4 per minute. So average waiting time in the system is 1 by 2 minutes by applying the formula. And then average number of persons waiting in the queue, that is we have to find that LQ, that is 24 by 144. And probability that a person arriving at a booth will have to wait in the queue, that's equal to 1 by 3. Next, in a single server queuing system with Poisson input and exponential distribution, is estimated that the mean arrival rate is 5 calling per hour. The inter-service time is exponentially distributed with mean 0.2 hour and the maximum possible number of calling units in the system is 3. Find the probability that an arriving customer has to wait. Second, probability of n customer in the system and the average number of customer in the system. So arrival rate is here 1 by 6. Service rate is 1 by 4. Probability that a customer has to wait for service equal to 1 by 6. And second, probability of n customers in the system is expected length of his waiting time is 3 minutes. And this all are the assignment questions and unit wise question bank.